I'm starting the recorder. I'm a little bit late today because I had to restart the computer. So what we'll do today is there are a few things. First thing is I'm going to have to cut the lecture a little bit short today because of all the activities out there. The person who would be tabling with me had a family emergency, so I probably have to do the whole thing solo. So the first shift, where my colleague was supposed to do, I might have to take over that shift too. So that means, we are probably going to be out of here by 9:50-ish or so. I will record as much as I can, and the lecture is going to be, very similar to the one from yesterday. So you can kind of watch the video from yesterday to kind of get the full context. The lab today is going to become a quote unquote homework, so it won't be a lab anymore. So you have until Thursday to get it done. So that gives you a little bit of flexibility. Typically, I won't do anything like this, but today is a kind of a special situation that I had to do that. Um, I'm just checking my email to. Oh, okay, so she will be there too. Okay, let me just reply really quickly. The display is in the office area. Okay, so we'll see how it goes. I mean, if my colleague says everything is good, then we might finish the whole lecture. But if not, I think I should probably still go help, because she had a family emergency and, it's she might need to go soon, after that. Okay. All right. So with that said, we are going to. So I will start with the lab today because I think I want to kind of turn the lab into a homework first. So we'll start with that. So the lab is called lab stack operations. It does not really rely on material that we talked about today. So you already have everything that you need to know to deal with this particular lab. But you only have 3 attempts. Okay, so in this one you only have 3 attempts. So keep that in mind. So let me go ahead and update the assignment first because this is not going to be a lab, it's going to be more of an assignment. So it's going to do on the 30th of October, which is 2 days from today, right before class. So that's 9 a.m. So that's going to be the due date. And I will turn off your IP filtering. You might need to write down the access code. It is LIFO, LIFO, but this lecture is getting recorded. Okay, so we are recording right now. And then we're going to change the due date to the same, which is going to be October 30th and 9 a.m. in the morning, October 30th, 9 a.m. in the morning. All right. So now that is set and ready to go. All right. So now the first thing I want to do today is to talk about how do we take on parameters with function calls and how do we return values in a function call. So that's going to be the focus of today's lecture. So the material that I am using right now, you can find that mostly in the caller-callee agreement document. So we'll go to the caller-callee agreement, which is right here. So right click and take a look at it. So the caller-callee agreement, particularly for what we're going to be talking about today, it is about parameters. It is also about, how do we handle a return value. So what we'll do is we are going to write some completely useless programs that make use of those, and then we'll take a look at the assembly language code corresponding to that. So we're going to use online GDB. I'm not even sure whether it will compile and work, but let's just hope that it would. Okay, so we'll go ahead and refresh online GDB, and it does not look like it wants to restart. I hope Amazon is not having another meltdown because that's what happened last time. That's okay. I got a backup plan. So I always have backup plans. Oh, okay, there we go. It's actually up, just a little slow. I don't know why. Uh, I don't think the problem is on my side because nothing seemed too sluggish on my side other than this web page. S- Yours is also slow? Just on online GDB or just overall? Just online GDB? Okay. Yeah, so that could be a issue specific to online GDB, and looks like it is okay now. Okay, all right, we'll keep using this until it doesn't work anymore. All right, so first thing first, I'm gonna pound include standard integer.h. So this way I can use types or type depths that are specific to the width of integers. Okay, so I'll define a function that returns a unsigned 8-bit integer. That's what uint 8 underscore t is representing. And we'll just call the function f. And in it, we are going to take two parameters. One is called x, okay, one is called y. Okay, so those are the names of the two parameters. And the function doesn't do anything other than to return, let's say, the addition or the sum of x and y. And then for the main program, it doesn't really do anything other than to call function f with, let's say, 34 and 75, 77 as the respective, arguments. And that's the entire program. So when people look at this program, especially from the perspective of Cisp 360, this program doesn't do a single thing, right? Because you call a function, the function returns a value, and we don't even bother to do anything with the value. So it would appear that this program is completely useless. So from the input-output perspective, that is true. This program is entirely useless. But from the demonstration of the concept perspective, well, guess what? It is not actually completely useless. Okay, so let's go ahead and take a closer look at this program because I think this is going to work out the way I think it should work out to illustrate the points that I need to illustrate. So I'm going to put a breakpoint right here. Okay, so right there. Come on, give me a breakpoint. Nope, it doesn't want to do it. Oh, there we go. Okay. All right, so we're going to go into the debug mode, and I forgot to specify the language. Oh, okay, I guess I did. All right, so the first thing we're going to do is just to run the program. Okay, so now we're on line 9. On line 9, we have to pass the two arguments to function f. So now, in this class, we have to start to think about how are the parameters passed to the function, okay? So some people may think, we're going to use registers, okay? The registers are visible from both the caller's perspective and also from the callee's perspective. So we can use registers. The problem with using registers is how many registers do we have? The ones that are software accessible. There are 4 of them, but we use one for the stack pointer already. So we only have 3 left, right? So do you want to have a language restriction of you cannot have more than 3 parameters of all functions? That doesn't sound reasonable to me. So that means, using registers, to pass arguments may not be the best option. Okay. Now, to be complete, okay, there are some aspects of passing arguments using registers, but for the most part, the flexibility is not there if you use only registers to pass arguments. So we'll go ahead and take a look at a few things right now. So we are going to take a look at the stack pointer. So in the x86 architecture, there is a dedicated register just for the stack pointer. So we can now print the stack pointer. And this is RSP. The name of the stack pointer is called RSP in the case of a 64-bit architecture. And it's hard for you to read, but we can sort of read the last few characters. It is FEA20. Okay, it's just a hexadecimal number, but we will kind of keep track of that too. And then what we'll do is we are going to single step into function f. Okay, single step into function f. And now we are on the only line in function f. So if x and y are only passed using registers, they should not have addresses, right? So we're going to take a look at the addresses of x and y. So print the address of x. Aha, it does have an address. And we'll also do the same thing with y. And it also has an address. Hmm. Okay, so now we want to look at the address Cs and see how they compare. So RSP, which is the stack pointer before the function call, ends with EA20. And we look at x, which is the first argument. It ends with EA0C, and then we look at the second argument. It ends with EA08. So that means the parameters actually live somewhere in memory. Okay, and more importantly, they're on the stack. Now, how do we know it is on the stack? Because we can print the stack pointer again. Okay, so when we print the stack pointer again, it is now at location EA10. Okay, so that is kind of interesting. Okay, well, it is interesting in several ways, but what we know is it was EA20 and now it is at EA10. And then for some reason, the arguments are actually below that, so that's a little bit mysterious to me because I think the new standard of passing arguments is not the same as when we had 32-bit architectures or 32-bit processors. All right, so when we complete this operation, if we single step one more time, it is going to compute x plus y. Okay, that's not a really heavy-duty computation, and it's going to return back to the caller. So now we're returning back to the caller. Then you guys go like, where's the result? Because we are not storing the result anywhere. So where is the result? So across, oh, great. I probably should have used my own debugger. Anyway, so the result is stored in a single register. Okay, for all the scalar type of return values, the return value is stored in a particular register. In the case of the 64-bit architecture, it will be the RAX register. Okay, so it would appear that I need to repeat this entire experiment using my own command line tool, which is okay, but it just takes a little bit of time to get back to. I don't have one that is. Oh, okay, this is the one. All right, fine. So we're going to take a look at return value.c. You'll just kind of paste the whole program back in. It's no big deal. We can do this. Return value.c, gdb, return value. So we are now getting back to the actual debugger, and this one is not going to time out because it is my program. So we put a breakpoint on line 9, run the program, you print RSP, which is the stack pointer. So we can see it's not exactly the same, but it's close. Okay, it's DD80 this time. And then we single step. Now we are in the function. So in the function, we can now say, okay, where is X? And also where is Y? So this time we can see that they are both below the stack pointer before, but the stack pointer itself also has changed to DD70. So when you look at the relative offset, of all of these things, they are about the same as before. All right. So when we single step one more time, it is going back to main. So now the question is, we are now back in main because I can say go list main, and it shows us that we are on line 11, and this is line 11, okay, which is right after the function call has returned. So now the question is, where is my result? Okay, where is the result that we have computed, which is 34 plus 77? It is in a register called RAX, okay? So we can now say, okay, show me register RAX, and it has a value of 111. This is in decimal. So the question is, okay, if you add up 34 and 77, do we get 111? Yes, we do. Okay, so this is showing us, how um, parameters are done. Okay, they're sitting somewhere on the stack. Two, we also know how the result of a return value is handled. It is put into a registered, in this case, RAX. So are those concepts okay? All right. So now we transition back to the documentation that I was referencing a little bit earlier. So I'm going to get out of this one, get back here. So we are going to look at the caller side first, okay? Particularly, we are interested in where are the arguments supposed to go? So that would be just this portion. Okay, so this portion says if there are arguments, the arguments are pushed in reverse order on the stack. The last argument is pushed first. So in the case of TTP, arguments are pushed contiguously with no gaps between them. And this implies the last argument has the highest addresses in what we call a call frame. So we'll talk about what a call frame is, in just a little bit. So now we transition back to the command line interface, and this time we are going to actually write the program. So we're going to say return, oh, okay, we'll do this. Return value.c, we'll copy that to return value.ttp-asm, and then we'll go to return value.ttp-asm, and then just comment out every single line here. So we are substituting the beginning of each line with slash slash and a space. So now everything is commented out. We start the execution with a no op because I want to use River Spider for this. And then we have a JMPI to main. And between that, we can pretend to initialize the stack pointer because the stack pointer or register D starts with a value of 0 to begin with, which is the proper value to start with. So this instruction here on line 2 really doesn't do anything that is useful, but I just put it here so that we can remind ourselves that, well, we need to double check that the stack pointer is starting at the right place. This is the entry point of F. This is the entry point of main. All right. And after main, for the time being, we don't treat main as an actual function. We just say, okay, when we get to the return 0, we just use a halt instruction because there's nothing to execute after that. So now we need to look at this function call to function F and to ask, okay, what do we do now? According to the caller-callee agreement, we have to push the arguments backwards, which means we push the 77 first, and then we push the 34. So that's why I need to say, okay, the first thing we need to do is to push 77, and then we push 34, and then we push the return address, and then we do a jump. Okay, so at some point, we're going to jump to the function, which is really just a JMPI to F. So this is not the only thing we have to do. The return address is pushed next, jump to the entry point, and then the callee should return to the instruction right after the JMPI instruction. If the callee returns a scalar value, the return value is assumed to be in register A. If there are arguments, the caller has the responsibility to clean up the stack space used by the arguments, if any. So in this case, how many bytes do you think will be used up by the arguments? How many arguments do we have? No, we have 2 arguments, right? We have 77 as an argument, we have 34 as an argument. And how many bytes do we need for each? According to the type in the C code, which we can still see, how many bytes are used up by each argument? Just 1, that is correct. So between the 2 arguments, we're going to use up 2 bytes. So to clean up those 2 bytes, the way we do it is simply to increment the stack pointer twice. Okay, we move the stack pointer up by 2 bytes, and therefore we reclaim the space. So this all has to do with what do we do when we push, and what do we do when we pop. All right, so we go back here, we push the 77. So in terms of the C notation, the most concise way to specify how we push is minus minus SP, the reference equals to 77. That's the C notation. But in order to do this in assembly language, we talked about this in the previous class. In order to do this, we have to load 77 into a register first, and then we decrement the stack pointer, which is register D, and then we do STDA. That's how we push 77 on the stack. So pushing 34 is going to be about the same, LDIA with 34, decrement D, and then STDA. So basically, this is the kind of operation that we're trying to do over here. So now we are down to pushing the return address. The return address would be the address right after the JMPI instruction, because this is where the called function should return to when the call function is done. So we'll give it a return label or return address label. You just put it here. So now we know what to push. So we have another LDIA, but this time using the label of return address 1, and then we decrement D again, and then STDA, so that we can return, we push the return address as the last item pushed, which also means the return address is going to be at the lowest address of all the items that we have pushed. Because when we push, we start at a high address, and then as we push, the stack pointer decrements. Are we still doing okay so far? Okay. So other than that, the fact that we are pushing the arguments backwards, last argument pushed first, everything in this program should be things that we are familiar with. Okay, because we have talked about all this last Thursday or before. Okay, so if this is new to you, or if any concept is new to you in this class, it means you probably need to spend more time to review the material. And also, it's not about the amount of time that you spend. It is also about how do you process that information as you review the material. If you want to talk about the techniques that you can use, we can talk in the office before class because I have office hour from 8 to 9. So you're always welcome to come to my office hour to talk about study skills and study techniques. So the caller side is all done. Okay, now we need to handle the callee side. So if you want to handle the callee side, you can also refer to the caller-callee agreement, and this is describing the callee side. The callee side says at the entry point of the callee, the stack pointer should point to the return address. If there are parameters, the first parameter will start at the address immediately or higher than that of the return address. The last parameter would be at the highest address within that portion of the stack, and parameters are contiguous in TTP. So if I were you, I would go like, tech, I'm not sure that is true. Okay, so show me how the stack looks like at this point. So the best way to do it is to simply put a halt instruction at the entry point of the function being called. Then you can use the trace to really see what is on the stack and how the stack pointer gets adjusted the whole time when we get there. Are we doing okay so far? Okay, at least an overall idea of what we are trying to do. Okay. So let's go ahead and do that, okay? And I'm going to try something that I might probably regret later on because I'm keeping this tab, on the editor, and I'm using a different tab to actually run the code. So this way I don't have to go back and forth all the time. The problem with this technique is not because of the tool, but because of myself. Because a lot of times I would forget to save the file first before I run the tool. So I'll be running an older version of the code without knowing it. We'll see. I'm pretty good at catching that, but sometimes I still do that, and yeah, it's not the end of the world even if that was to happen. So I'm just submitting the job to the spreadsheet, so it would go through the assembling. Oh, it didn't like it. Hmm, that's fine. If it doesn't like it, we go to the assembler, go to the source tab to figure out why it is complaining about it. Oh, it is not using the right code. I think I just made my famous mistake, forgetting to save the file. I did all of this work and I forgot to save the file. Now, how can I double check to confirm that I just forgot to save the file instead of I hallucinated for the past 20 minutes? I actually did not do anything. Well, I think it's Control G would do it. So when you're in VI, Control G will show you the current status of the editor. And quite clearly, it says it is modified, which means it is not saved. There are some modifications that are not saved. So I just made my most common mistake. Okay. You may not be making the same kind of mistake, but I do that all the time. So that's why it's the first thing that I do is to check, did I save the file? Okay, now that it is saved, it doesn't show modified anymore because now the content of the buffer, which is what we see now, is consistent with the actual content of the file. Okay, so now we switch it back here and go like, okay, let's try it one more time. So I think this is going to work. We'll see. All right, looks good. Okay, so now it's actually running the code. The code is all done. We switch back to the assembler. Okay, we can see there's nothing, no error reported this time. So we go to the analysis tab. The analysis tab is really one of the best way to visualize the execution of a program. Even though it doesn't really show you the content of the stack, you can still easily see how it is all done. So I really like when people kind of sign in also, because you can actually take a snapshot now. Okay, if you want to take a snapshot, go to File and then go to Make a Copy so that you can make a copy of the Google Sheet onto your own Google Drive. Okay, so this way you have your own copy. You can modify, you can comment, you can add annotations, all you want. So, but we are going to focus on the execution of the program step by step. There's nothing to say about this, okay? We are at location 00, okay, which means the program counter is at location 00. It is corresponding to line 1 of the source code, and the actual code on that line is a no op instruction, which doesn't do a single thing. That was kind of the whole point. But we need that in order for the simulator to work. So this one also really doesn't do anything particularly useful because register D starts with a value of 00. We're just double checking and make sure that, okay, it is definitely 00 at this point. Okay, so not really terribly useful. It's more of an annotation purpose. So now we JMPI to main, which means we are continuing execution at main, which is starting at location 06. The first thing it does is to do an LDI A77, so the A ends up with hexadecimal 4D. So hexadecimal 4D is 4 times 16. Okay, this 4 is the number of 16s, and D is a 13. So 4 times 16 is 64. 64 plus 13 is in fact 77. So the hexadecimal representation of 77 is 4D. Okay, we just double check that. And then we decrement the stack pointer to allocate a byte on the stack. So as a result of the decrement, the stack pointer is now FF, which is corresponding to 255. So if I were you, I would also use another spreadsheet perhaps to keep track of the content on the stack, just so that it is visual to you. So what that would look like would be something like this. So let me go back to my folder and go back to the part that you guys can see. Go to share the shared portion. And I'm going to create a new spreadsheet for today. So if you have a computer in front of you, you can also open this up right after I give it a name. So this is 1028. So now you can go ahead and open this one too. So what I want to do here is to basically say at location 255, what do we have there? Okay, what is the content at that location? So we now know that it has a content of 77 in hexadecimal. Nope, it is 4D in hexadecimal, which is 77 in decimal. But we also want to kind of document what it is. Okay, this is basically the second argument, which is also known as parameter y from the perspective of the callee. Okay, so now what about the next location? Well, we can go back to the trace. So once we push it, okay, we now know that the location FF is overwritten by the content of 4D. So this equal as opposed to the double equal here, it is intentional. A single equal means assignment, which means whatever is on the right-hand side is used to update the left-hand side. In this case, the left-hand side is a dereference of FF. I know, I should have used 0xFF and typecast the whole thing, but I don't want to use a lot of space on the column. So asterisk FF simply means the location, the content at location FF. It is now changed to 4D. So the next thing we do is we load 34 into register A. Okay, 34 is 22 in hexadecimal because it is 2 times 16 plus 2. And then we decrement the stack pointer. The stack pointer is now FE. And then we do a store instruction. And as a result of that, FE or location FE is now getting the content or the value of 22 in hexadecimal. So in the table that I just created over here, now I go to location 254, which is FE in hexadecimal. And I say, okay, the content is now a 22, but what exactly is it? It is the first argument of the function call, otherwise known as parameter x, from the perspective of function f. So are we still doing okay so far with the explanation? We good? Okay. All right. So what is happening next is location 253. It is getting the return address. So for the return address, we can just kind of use the name return address one because it kind of floats around depending on the other instructions. But we just have to kind of document this and say this is the return address. And at this point, okay, that's where the stack point is pointing to. So if I go back to the assemble tab, okay, we basically push this is the return address. And by the time we get to the halt instruction in function f, this is what the stack looks like. Okay, the stack looks exactly like this. The stack pointer is pointing to the return address at location 253, which is also known as FD. And then we have the next location being parameter X, and then the next location being parameter Y. So are we still doing okay so far? Okay. So this particular demonstration is not only about how parameters are handled and also, how, the stack looks like. It is also about the tool itself. Okay. It's also about how you can use the analyze and the analysis tab of the assembler to kind of follow along with the execution of the program because this is, I think, the best tool for debugging programs, for later on in this class. Okay, this is the tool to use. So with that said, we go like, okay, cool. So now what do we do? Okay, now that we know the content is correct at this particular halt instruction, so what we'll do is we're going to use a few labels. Okay, so I will first talk about the label first, and then we'll talk about what they actually mean. So LVS stands for local variable size. Okay, it is telling me the number of bytes that I need for the local variables. Well, in this case, we don't have any local variables. F has no local variables. So LVS is going to be a 0. Now, if you prefer to spell everything out, you are more than welcome to change all the LVS to local variable size. I just do not enjoy typing all that much, so I'm going to use LVS. All right, so the next thing is after the local variables, we are going to have parameter x. So f underscore x is going to be f underscore LVS 1 plus. So the 1 plus is basically handling the return address itself. In other words, I'm trying to keep track of the offset of where I can find local, not local, where I can find parameter x from where the stack pointer points to. Let me say that one more time. The label f underscore x is denoting the number of bytes from where the stack pointer points to, so I can find x as a parameter. Are we good so far? Okay, I can show you exactly how it looks like in the case of the stack here. The stack pointer is 253 at this point. Where can I find parameter x? Location 254. So when you subtract 253 from 254, you get 1. That is what f of x is trying to represent. Is that okay? All right. So now we switch back to the code here, and I need also to know where to find y. So this would be f of x or fx 1 plus. And once again, we're using postfix notation. So f underscore x 1 plus is really the infix. It is equivalent to the infix version of fx plus 1. Okay, but we are using postfix here, and you can probably use AI to kind of explain to you, give it a certain infix notation expression, and it will show you and explain to you how to convert it into postfix notation. So, you can, if you're interested in doing this and want to know exactly how to do it, that's how I would do it, is to kind of have the AI to help you out in the conversion process. But the definitions on line 8 to line 10 doesn't really do anything other than telling the assembler itself and go, every time you see f underscore x, it means 1. And every time you see f underscore y, it means 2. That's all it does. Okay, it's just defining some labels. So when we try to implement the instruction or the line here, which is x plus y, the first thing we need to do is to go like, okay, I know the offset of parameter x from where the stack pointer points to is f underscore x. How do I start from that to get to the actual value of the parameter? So the template to do that is to put the offset into a register. You can use register A, B, or C, okay, for the most part. So right now, I can use register A. So what that does is register A is now the address of parameter X minus the stack pointer, because f underscore X is an offset from where the stack pointer points to where I can find X. So it is just an offset, and that's why I have to do a subtraction of the stack pointer to correctly document what is in register A. Are we doing okay so far with that notation? Okay, it is an offset. So now, from an offset, how do I get to the address? Well, as it turns out, if you understand algebra, that's not really too hard, okay? Because if you do algebra, you just go like, well, this is what I need. This is what I got. So to get to what I need, I just need to add the stack pointer back to it, right? So now, register A has just the address of X, which is the parameter. But what I really want to add here is not the address of X. I want to get to the value of X. So that means I need to dereference it. There are only two instructions that are useful for dereferencing. LD is one, ST is the other one. But LD is the only one that's reading. ST is the one that is storing. In this case, we just need to read. So this is how we do it. So now register A is the dereference of the address of X, which was what it had, which turns out to be, oh, that's just the value of X. So, okay, so let's just say that you are not convinced at this point, okay, of what the program is doing, that we actually have the value of parameter X stored in register A. Put a halt instruction here, run the program again, okay? So this is also why, I think it is important to install um, Reefer Spider on your own computer, or at least put it on the thumb drive. It does work from a thumb drive. So that means, if you use the lab computers here for all your lab, you can install Reefer Spider on a thumb drive. Okay, take that thumb drive, to the computer, plug it in, and you have access to the tool. So that makes it kind of handy because you can use it in the lab, you can use it at home, you can use it in the library, you can use it on your friend's Windows computer if you want. So I think it's kind of cool. So we're going to rerun the program, okay? And just kind of go through those 3 lines of code and see what is happening when we execute those 3 lines of code. So we now get back here, we go back to the assembler, and then we go back to the analysis tab. And where we left off earlier, I think I just made my famous mistake of not saving the program again. I do apologize. Control G, yep, I did that again. All right. I probably need to make this a command in Vim itself. So this way I just run the whole thing from inside Vim. Then I don't have the problem of separating the editor from actually running the program. All right, fine. Okay, now it's working. So we can see how all this instruction is doing is to put the value of 1 into register A. But since the stack pointer is FD, FD plus 1 is FE, and that's why register A ends up with a value of FE after the add instruction. So now we go back to the stack visualization and ask what is at FE? It is the 22 in hexadecimal, which is the value of parameter X. But we are still one step away from what we really want because we want register A to have the value of what is at the location FE. So the LD instruction accomplishes exactly that. So now we have the value of parameter X in register A. Are we good so far? So I'm going to also add a little bit of information that is not specific to the topic that we are talking about. This is how I would study in this class at this point. Okay, is to go through these traces and be able to explain clearly what is happening on each line and how the different lines work together to get something done and relate that to the C++ concepts that you have already learned. Okay, that is how I would study for this class. Okay, there's no quote unquote written material that you have to read or memorize. Okay, it is all about applying what we have learned already, all the instructions, the concept of a stack, and so on and so forth, and kind of put them together and relate these low-level implementation to concepts that you already understand in CISP 360. Okay, so that's kind of the focus of how of this class, for the until the end of the semester. Okay, so now that we got this part done, we can go back to the source code and go like, okay, let's finish this. So now we need to do the same thing to parameter y, because this is what we need to do. I got the x taken care of already. I need to take care of the y. So you can probably imagine it's not really super duper complicated. But I do need to use a different register because otherwise I'll be overwriting register A, which already has one of the components that I need. So I just need to use register B. I could have used register C. It doesn't really matter. You just have to use the register consistently. All right. So I'm saying that at this point on line 19, register B would have the value of parameter y. So, and one other thing about debugging this kind of program is do it gradually. Okay. Do not try to write 20 lines of code and try to debug 20 lines of code. Okay. I cannot do that in assembly. Okay. So write a few lines of code, put a halt instruction in, check the outcome of the program, make sure it happens the way that you think it should happen before you proceed. But I can also tell you every time I teach this class, I would repeat that instruction, and I would say maybe 5% of the class will try to follow that advice. The rest of the class will try to write the entire program. All I mean, the longest program you're going to write at this point is about at the most 100 lines. But 100 lines of assembly code is not the same as 100 lines of C++ code. Okay, the debugging process is entirely different. So now we get 4D, which is our 77 in register B. So all we need to do is to add those two, right? Okay, so we'll go ahead and finish up the program. And there we go. So we just need an add instruction. Okay, so the add instruction could have been BA or AB. I'm going to do AB because the sum is supposed to be stored in register A as the return value. That has to go back to the, let me see, which one is it? Yep, it has to go back to the caller-callee agreement because in the callee-callee agreement, in terms of the callee, okay, I think I was using another tab, which is this one. So in terms of the callee, if there's a return value, the return value should go to register A, and that is explained here. If the callee has a scalar return value, use register A to return the value. So that's why I want to put the sum in register A and not in register B. So after this, the callee is responsible to pop the return address and then use the return address to return to the caller. That is something that we have done last week already. So I'm not gonna spend too much time to okay, I just re okay, redo. Okay, and redo one more time. Oh, no, that's it. All right, so at this point, I can do the return code. We have an LD. So do not use register A because at this point, register A has its special purpose of specifying the return value. So do not overwrite register A from this point. You can still use register B or register C. You still get a choice here. So I'm going to use register C. Okay, I'm retrieving the return address. This is how we pop the return address into register C. So don't forget to increment D because otherwise you just retrieve, but you did not deallocate the location. And then JMP C is going to continue execution at the caller. This halt instruction becomes useless. So now when we get back to this instruction, this increment D instruction, register A should have the sum of the entire thing. So we'll go ahead and make sure that I save the file and then run this whole thing again and just double check. So this time our focus is going to be on line 48, and we make sure that register A has the value of 77 in hexadecimal. And if that is the case, then we should be all good. All right. So we switch back to the assembler in the analysis part, and if you want to follow everything, you're welcome to. Like, how do we pop the return address from the stack, how do we deallocate that location, and how do we actually perform the jump. But the key point here is this is line 48 in the source code. The last time we update register A is to update it to 6F. So I stand corrected. It's not 77. It's supposed to be 6F because 111 is 9 times 16, which is 96, plus 15. That's what the F is. So 6F is correct. I stand corrected. It's not 77 in hexadecimal. But are we good so far in terms of the execution of the program? Okay. So I know I did this kind of in a rush, but I did cover all the material that I intended to cover in the original 80 minutes, and I kind of shrunk the whole thing to about 46, 47 minutes. So I know it's a rush, okay, but it is recorded, okay? I will upload it so that you can watch this again, along with the lecture that I also recorded yesterday for the Monday, Wednesday class. So you can watch that one as well, okay? And then the lab today, once again, is not going to be a lab. It is going to be a homework. So you have until Thursday at 9 a.m. to complete the whole thing, but you still only get 3 attempts at it. Okay, so be very careful about doing that. Um, the other thing you can also do, okay, is since you all have access to Gemini at this point, is you can take this whole thing, okay, and if I were you, I would go to the source document, which is in Markdown format, upload it to Gemini, okay? Then you can interact with Gemini specifically based on the description in this particular module. Okay, so this way Gemini can offer you, some additional explanation if you need to that is specific to this class. Because otherwise, if you ask Gemini a general question of how the stack pointer is going to be used, there are a few standards out there depending on the architecture. So Gemini can give you the wrong answer if you don't say, okay, we are specifically talking about the TTP ASM and tax way of using the stack. So this document is really important for that purpose. Okay, so that's my advice. Okay, is to utilize AI to help you understand the concepts. You are more than welcome to also upload, the other modules too. But I would say the most important module to upload is the caller callee agreement. Okay, that is the key document to utilize, as well as the calling and returning from subroutines. So upload these two modules to Gemini or make your own jam. You guys know what I'm talking about when I said make your own jam? GEM, gem. Yeah, you're it's kind of like a notebook LM in the sense that you are limiting the AI scope of knowledge to what you just upload so that it doesn't try to go out to grab whatever is on the internet. So I think making a gem out of the modules would be a good thing to do. Yes. It'll be the same as a custom GPT in the case of Chat GPT. So a project, is a container, but I'm not sure how a container works with custom GPT. So I've only used custom GPT where you can upload a bunch of files up to 20, I think. Gemini can only upload up to 10, not 20. But you can make concatenation of the files, the markdown files, and it would actually know the separation of the markdown files. It would recognize the actual boundary. So you can concatenate a bunch of the markdown files, turn it into one single file, upload it to the gem. So now every time you use the gem, it would only use that context. Yep. Alrighty. So as I mentioned a little bit earlier, I'm gonna have to cut the class a little bit short, okay? But that also gives you guys the time to participate in, the STEM quad. Yes, go ahead. The code for the lab. It is LIFO, LIFO, all lowercase. LIFO. And the recording is going to be uploaded right now. I'm going to stop the recording now.